Okay, so we are continuing with random parameter estimation. So this is lecture number 30. Actually, in this course, we are more interested in random parameter estimation. So I'm giving this earlier maximum likelihood estimation results for the basic definitions on estimators like unbiasedness, consistency, etc. Now, in the random parameter estimation, what do we have? So again, we have such a picture. So theta is quantity of interest, is a random variable with prior distribution, this, okay? Like in the very first example that we have discussed, theta takes 3 values and their probabilities are as such, okay? So that is the prior distribution that I'm talking about. Now what do I have? Now again, I have these observations. Let's show these observations by x. So this is the observation vector. Okay. Observation vector x. So what's our goal? The goal is to minimize, expected value of theta, or let me write before this, let me write cost theta hat of x, okay? So what's going on? So I'm assigning a cost, you may say assigning a cost to an estimation error, you may say, okay? So what do I mean by this? So for example, my cost function, it has two arguments, x, let me write theta 1 and theta 2. It has cost has two arguments. So what do I have? So theta 1 minus theta 2 is over here, and you may have square error as your cost, okay? So your cost is theta 1 minus theta 2 parentheses square, okay? Even though this is a function of two arguments, only difference matters in the calculation of the cost. So what does that mean? If theta 1 is equal to theta 2, the cost is 0. It doesn't cost you anything. But if you are deviating from this 0 location, equality case, theta 1 is equal to theta 2, by some, let's say, error of delta, now your cost becomes, deviation by delta, has delta square cost on you, okay, delta square. Of course, there can be other cost functions, like there can be a cost function like this, okay. So this is theta 1 minus theta 2 in absolute value, okay. So this is then costing you delta. Okay, so you may wonder, how can this be? Well, maybe they are meeting this blue curve and this black curve. This is the location of 1 and minus 1. Okay, so when deviation is 1, both of these curves, meaning cost functions, they give you an error of 1. So let me then correct this like this. Okay. So as you see, depending on your cost function, your deviation from the true value is penalized differently. This is like a penalty function or cost function. It's penalized differently. So you can imagine that I can have many cost functions, provided that is something like a monotonous increase from both sides, from this 0 to the left and to the right. It's like monotonously increasing. Okay. So there are issues about how we, what is the properties of these cost functions and so on, how we select those cost functions. But in this course, we will be mostly using the square error as our cost function. So let's assume square error is selected as the cost function. Then let me call this is called risk. Okay, or let me call this just R, and this R denotes the risk. Okay. Then R becomes, in this case, for the square error, theta minus theta hat. It's just, like the earlier case, isn't it? This is our error variance for the unbiased estimator that we have previously discussed. Okay. So this is our risk, and so on. But the important part, this one, is now theta is random. So previously we were taking expectations over x only, because x was the observation vector. Theta was non-random. Now I'm taking expectations over theta and x vector. Okay. So this is this. The goal is finding an estimator, this, such that risk is minimized. Okay. So previously we were discussing maximum likelihood principle. It's like an approach. Okay. It doesn't have any optimality properties other than this asymptotic optimality properties. But this one, well, it has a very well-defined optimality properties. So what do I mean by this? So let me write this risk one more time. So this is expected value of. So how should I write this? Let me write it like this one. X, expected value of theta given x. Theta is, okay, random quantity given x. Theta minus theta hat x, parentheses square. Can I do this? Of course, this is the definition of conditional expectation, isn't it? So I'm fixing this x value, I'm writing this conditional expectation, and so on. So if you don't remember what's going on, if R is equal to expected value of some argument, and this is like, let's say, xy, x and something else, then this is nothing but, fxy, xy, then let me call this, for example, h of xy, dx dy, double integral, let's say, something like that. But I can write this as x density times conditional density y given x. Okay. So if you do that, then you move this x out, it becomes then this density. You move it over here. So you integrate, you take the expected value of whatever remains, that becomes this conditional expectation over this conditional density, and that is it actually. So let me erase this, and let me try to write this in terms of expectations as I have already written. So this is density of x. I'm integrating with respect to x. How about this one? So this is density for, this theta. Theta, okay, minus theta head of x, parentheses square, fx, sorry, theta given x, theta given x, and I have d theta. Okay. As I have said, if you combine, if you move this marginal density of x inside of the second integral, then you have joint density of x and theta over here. And this is nothing but this. Well, what is interesting is this. Let me write dx also. Okay. Now, this is maybe a multiple integral. I have multiple observations. Let me mark it like that. Okay. So what is interesting is, this is the critical part actually. Let me call this I theta hat. So what do I mean by that? Well, for the sake of this integration, as you see, x is constant for the sake of this bracket. So this bracket assumes that x is just a constant value in the range of this integration. Okay. Maybe it's a vector, doesn't matter, but it's just a constant. Okay. So let's assume that, of course, then this theta hat is function of that constant, but since it's constant for the sake of this integration, maybe I don't need to even consider any variation of x. Now, what is our goal? Our goal is, finding this estimator. But you see that this is the contribution to the risk for a given x. What do I mean by that? So the final evaluated risk value is nothing but the mean value of this function, meaning that there is some error for every x, this integral result, inner integral result, and I'm summing up those I values for different observations, and that is it. Now the critical idea is the following. If I minimize this second inner integrand for a fixed x value, if I can find a formula for that, then I'm doing my best for every observation, isn't it? So the problem decouples essentially. So if x is fixed, the second integral is minimized, you change x to another value, the second integral is again minimized for that x, then their sum, the error will be their sum, weighted sum according to this density. It will of course be minimum because we are piecewise minimize all possibilities for different x values. Okay, that is a critical observation, and it all depends on this conditional expectation, as you see. And this is nothing but, no surprises, this is previously we have defined, this is called posterior density. Okay, this part is the posterior density. So let me try to then minimize that I function, the inner integrand, for a fixed x value. Okay, let's minimize I theta hat. I'm not writing even this dependency on x because of course estimator depends on the observations, I know that, and it's just constant for this discussion. For a given, let's say, observation vector x. Okay, so for the sake of simplicity, let me just write this as c. Okay, this is just a constant. So let me write this. So I theta hat is equal to theta minus theta x parentheses square f theta given x d theta. Okay, this part. So I want to call this one as, where is it? C. So just for shorthand, because I don't want to write it again and again. So I want to minimize this with respect to C then, isn't it? Because at the end, theta x is fixed. When x is fixed, maybe it's a vector. If it is fixed at the end, I produce a single estimate, and that estimate be C, whatever the value of C. So to optimize that, what should I do? I should take the derivative with respect to C and equate it to 0. So I have minus 2 also over here. And equate to 0. Okay, so I'm taking derivative with respect to the C estimate for that given observation. As I have said, for a particular observation, I'm trying to find the optimal estimate. Okay, we have done something like that before. For this observation, what is the best estimate? Okay, inverse mapping. So this should be the case for that estimate. Then let me write it over here. So this is just C. Okay, I end up with this. So this minus 2 cancels with this 0. Okay, so if I theta times this density is present over here. Minus c times density. C is just a constant for this calculation. Take it out and move it to the right side. So I get this. So what is this? Well, we see that this is equal to the conditional mean. Or let me write it more specifically. This is, okay, x random vector. Okay. So this is conditional mean. Again, I'm using capital X. Remember our previous notation. Capital X vector denotes the random variable. When this capital X random vector is equal to our observation vector, I calculate the mean of theta according to this, conditional mean. Theta given x is equal to x. Conditional mean. So let me write this bigger. Theta given x is equal to x. And this is what's called conditional mean. Okay. Well, that is it. So what we see is that the conditional mean of theta random variable. Okay. So what do I mean by that? I calculate this posterior density, which is this, and then I evaluate its mean value. That is it. That becomes my estimate. So theta hat of observation is equal to the expected value of theta given x. I think it's clear. Is the optimal estimator. Minimizing mean square error. Okay, optimal estimator minimizing this mean square error, and this is called Bayesian estimator. I mean, such an estimators are called Bayesian estimators. Okay, so let me maybe mention this Bayesian estimator at a later time, not to confuse you. So our focus is right now construction of this, conditional mean, and what is the meaning of this conditional mean operation. But before that, well, let me maybe do a sketch. So how can I sketch this? Well, let me do something like this. For example, my observation is x. Then for x is equal to 5, let's say, I'm trying to sketch a density over here. Okay, so over this line. Okay, so this is like a three-dimensional plot. So, okay, so it has a z-axis in this direction. Okay, so you see that when x is equal to 5, there is a peak value. So let's say it's theta. When this theta is, let's say 5 and theta this. Okay, theta hat 5. Okay, so what do I mean by that? So this is what I mean by conditional distribution. X is equal to 5. So this is what I'm trying to sketch. This is the Gaussian distribution, let's say. Gaussian distribution, maybe this is something like theta, this, it has some variance, sigma, theta square, let's say, theta hat square, and so on. Okay. But the important thing is the following. Right now, this is a conditional distribution of unknown quantity given the observation. It has a shape like this. So you are only interested in the mean of this. Okay. Of course, it's a distribution, but I'm only interested in this mean of this posterior distribution. And now, when theta is equal to, let's say, 10, I hope I can sketch it good enough. Let's say that it is a distribution, again, something like this. Okay. When observation is equal to 10, then this is again density of unknown quantity when the observation is equal to 10, and let's assume that this is something like, you know, again it has a mean value for 10. Okay, so I'm processing this, and this, it has a variance. I don't worry about that variance, but this is mean value. Now if I sketch a curve, something like this, is passing from here, and so on. Okay, so what is this curve? The green curve. So let me correct this part. Okay, so this green curve is expected value of theta given x. Okay, so this is a function of x, obviously. So what do I mean by a function of x? If x is 5, then this shaded green curve passes from this point. If x is 10, it passes from this point, and so on. So what does those points correspond to? They correspond to the mean value of this conditional density, this theta given x density, or it's the mean value of this what we call posterior density. Okay, and this is actually our estimate. Okay, this becomes our estimate, and this curve is called regression line. Regression line. Okay, and what else? This is called conditional mean estimator. So let me see. This is called conditional mean estimator. So I think with this picture, it's a little bit more clearer that what we are trying to do. So when observation is equal to 10, okay, then I calculate this density, x is equal to 10, so it's this red density. So the mean value of this red density, which is, you know, this abscissa is 10, then ordinate is the mean value of that density, and that mean value is our estimate. This is called conditional mean estimator. Okay. Obviously, as x changes, you repeat this process, you get different values for the estimate, and so on. Okay, now I want to briefly discuss some properties of this estimator. Okay, this is very important actually, because as you see, this is the optimal estimator, minimizing MAC for this problem. So its optimality is not asymptotic, and so on. As you see, there is no bias considerations and so on. So this is the optimal. You can never beat this. So properties of conditional mean estimator. I'm talking about conditional mean estimator. Now let me see. Number one. If we want to estimate, let's say theta, beta, gamma, etc. So more than one, let's say more than one random variable from, let's say, x vector, then what can we do? Then theta head of x is expected value of theta given x. beta hat of x, expected value of beta given x, and let's say this is gamma hat of x so they individually minimize MSE for, let's say, theta, beta, and gamma estimation error. So as you see, if you want to use x to estimate, let's say, like in our earlier problem, one of our earlier problems, theta can be amplitude, this can be phase, this can be frequency, and you're interested in the amplitude estimate, phase estimate, frequency estimate, and so on, from the same observation, okay? Then, of course, if you do this for specific known amplitude, then this becomes the optimal amplitude estimate, okay, in terms of MSE minimization. So what we see is, well, let me use this. So if we define, let's say, a theta vector with some abuse of notation, theta, beta, gamma, okay, then expected value of theta vector given this theta vector, given observation x. Okay. Now I'm trying to define a random vector for the desired quantities. Then, theta hat is equal to this. And let me put it in a box. Given x. So this is the conditional mean for mean vector for desired random vector theta, okay? So this time I'm calculating the mean of this conditional mean, this calculation, conditional mean of beta, this calculation, and conditional mean of gamma, and concatenate them. Then I denote that result as my estimate for this vector, okay? Let me define this as theta vector. Then this becomes my estimate, okay? Theta estimate of this according to the conditional mean operation. Okay. Clearly, expected value of theta minus theta hat. So this is the Euclidean norm. Okay, x. This is theta and x is equal to, if we write, well, I think, okay, clear, is minimized with the conditional mean vector. Okay, I'm talking about conditional mean vector over here. So what do I mean by this? Now this is risk for the estimation of, let's say, three quantities. And this is nothing but, in this case, theta, beta, gamma. Okay? So this is nothing but their estimates. Theta hat, beta hat, and gamma hat. So if I write this for this specific case, so this becomes theta minus theta hat parentheses square plus beta minus beta hat parentheses square and gamma minus gamma hat parentheses square, obviously, okay, because this is the definition of the Euclidean norm, okay. So I take the difference of elements of this vector and take their square and sum the results. Euclidean norm definition. So you see that I'm generalizing MSE for a single variable. You may say this is like the total MSE of this desired vector, total MSE, summation of individual MSEs. Okay, so we may call this total mean square error. Okay, if you wish. So this is just an observation. Very good. Actually, we haven't done anything other than repeated the same argument. Number 2. So what is our second case? 2 is very interesting. Now orthogonality. Let's say that theta is equal to, so this, okay, theta vector estimate is equal to expected value of theta given x. So this is conditional mean estimator. Conditional mean vector estimator. So this is our optimal estimator. Okay. Let g of x a vector valued function of observation. Vector valued function of and observation x. Okay. So clearly this is our estimate. This also depends on x. Now the result is as follows. For any gx function, we have expected value of, this is theta minus theta hat, okay, of x. This is the vector g of x with transpose is equal to the 0 matrix. Okay. So what is it? This is like a general result. So this is the error vector. Let's say in our case we have, let's say, on the 3 terms, theta, beta, gamma. So this is the error vector for this one. So how about this? Now I have an observation processed by this g function. Okay. So this g function must be g1 of x, g2 of x, let's say m of x. Okay. So this is a vector valued function. Actually g is also a vector. Okay. So it takes a vector as an argument and results a vector. So this is this g vector after processing x transpose. Okay. So the result is this 0 matrix. Okay. In this case it's a 3 by m matrix because this is 3 by 1. This m is dimension of this vector. Okay. So we have in this case 3 by m, all 0 matrix over here. So what is the important result is this? Well, actually quite surprising if you say it this way. Let me say it. So estimation error of optimal estimator is uncorrelated with, so the estimation error of optimal estimator is uncorrelated with any possible processing of any possible linear, nonlinear processing of observations. Is this clear? Well, this is error for theta, the first one. So this times a processing G1 of observations is equal to 0 after expectation. Okay. Similarly, this GM is equal to 0 after. So you see that, this estimator is quite remarkable. So the error, you may say our estimation error, remains uncorrelated, not only with the linear processing of observations, but also for any nonlinear processing of observations. So you may say that there is no, information left by nonlinear processing in terms of extraction to improve this estimator, because whatever you do, your estimation error remains uncorrelated. Okay? So please remember that this correlation is telling us some kind of dependence between two random variables. So if they are Gaussian, for example, they remain independent. They would be independent. Okay? Uncorrelatedness means independence. So what we see is that for any G this happens. So that is a remarkable part. So how can we prove this? Proof is actually very simple. So we are trying to prove the following. Expected value of theta G transpose X, is this equal to expected value of G transpose of X. Okay. So let me move this over here for the sake of using this part. Okay. So I'm expanding this. I'm multiplying by G transpose. G transpose times theta hat, move it to this side. Okay, it becomes this. And the other term is this one. So what am I going to do? So this is an expectation over theta and X. So again, let me write as two expectations. This is called iterated expectation. Of this. So if I do this, now this is just, as you see, conditioned on X. It's just constant, so I can take it out of this. Then this is expected value of X, expected value of theta given X of theta, okay, times G transpose X, okay. So I'm left with this. So how about this one then? Well, this is conditional mean, isn't it? Conditional mean. And I have called my conditional mean as this is the optimal estimator. So this is this. It is equal to this one. So I get equality of expected value of theta of X, G transpose of X, and I have this. That is it. That is the end of this calculation. So we see that indeed, after this operation, I immediately get this result. So for any G function, this is satisfied. So the critical step is, because in this product form, if you separate this, if you do this separation, conditional density times the marginal density, well, whatever you have over here, you replace by conditional mean estimator because of that, okay? So your theta over here immediately becomes theta hat, and then you have this equality, theta becomes theta hat over here. Okay, so this is interesting. So let me do the reverse. So what's the reverse? Also, so this is the reverse argument. If expected value of, I'm trying to write this, theta minus theta hat x G transpose x is equal to the zero matrix for all G functions, then this should be the conditional mean vector estimator. Okay, so how can I check this one? So let's assume this is true. Let's say proof. Expected value of, so I'm assuming that this is true and I'm trying to reach this. Theta minus, let me see, theta, okay, theta G transpose x is equal to theta hat x G transpose x, okay? So this is, well, so what is this expectation? This expectation is over this random variable x, because there is nothing else. So how about this one? This contains both theta and x. You should be a little careful, theta and x, as you see. But this one is expected value of theta given x. Oh, sorry, I shouldn't be writing that one, sorry. So let me think. So let me first of all write this like minus. This is equal to the zero matrix, okay, the same thing. Then, okay, then let me try to write this, okay, this is good, expectation over x, then expectation theta given x, one more time, very similar trick, theta, okay, let me write this, G transpose x, minus theta hat of x, G transpose of x, this is equal to the zero matrix. So what did I do? Again, I have introduced this conditioning operation, okay? So if you evaluate this first part of this expectation, this part, you get this term, okay? Then minus expected value of the second part, you know, first term minus the second term, okay? But again, for the sake of this expectation, I can take this one out, okay? If I take that one out, I end up with expected value of x am I right? This is the zero matrix, okay? Because I can take this one out. Once I take that one out, then I can collect these terms with the common bracket of, with the factor, this G transpose x. Now this result says that for all G, I have this equality, then set G is equal to, G of x is equal to, I'm setting it to this, expected value of theta given x, okay. So, because this is valid for any G function, why not select this function as my G? It's possible to do that. Then what I see is the following, expected value of, this is G of x, G transpose of x, this is equal to 0. So how can this be equal to 0? G times G transpose. Well, if you check this diagonal terms of this matrix, okay, then this is only equal to 0. G times G transpose. So let me briefly write this. So let's say that G of x is G1, G2, G3 of x. Then this is equal to 0. That means that expected value of G1x square, G2x square, G3x square, and of course I have G1, G2s and so on, G1x, G2x and so on, but all of them should be after expectation is equal to 0. So what do I see is that, this should be equal to 0, this should be equal to 0, this should be equal to 0. Why? Because this is always positive right now. If this positive quantity is equal to 0, then that quantity, I should say non-negative. If you take square of something, you get non-negative values. If this non-negative value is equal to 0, that function g1 of x should be equal to 0. So from this result, we see that then what we have, this should be equal to 0. So all of these, this should be G1, G2, G3 should be equal to 0. Then this vector should be equal to the 0 vector. Then this is equal to theta 1 of x. Okay. So this is the conditional mean vector. So what do I have? So I have started with this statement. If I have such uncorrelatedness property for this random vector, then I see that this property implies that this estimator be the conditional mean vector estimator. Okay? Because otherwise, this logical sequence cannot be followed. Okay? The critical part is for all g functions. For all g functions, this estimation error is uncorrelated with the processing of observations. This is the critical part for our purposes. Okay, so let me have an example, maybe a somewhat more numerical example. So let me erase this. So let's try to do the following. So this is y, this is x, 1, 1, minus 1, minus 1. So this is joint density of fxy is equal to, let's say this area is 1, this area is 1. So this is 1 over 2 over shaded area. So this is uniform over the shaded area, isn't it? So what do I mean by this? Actually, this is something like this. Okay, x, y, z is the value of this, joint density. Now, when x is 1, y is 1, I am over here, and I have negative quadrant also. X is negative, y is negative, so this is Okay. So what I see is something like this. On top of this, I see a box of height 1/2, and on top of this one I see another box. It's a three-dimensional plot of height 1/2. Okay, is this clear? So this is the base of those boxes. So this blue marking parts is the base of those boxes. Okay, so this okay. So the volume of these boxes, two boxes, is equal to 1. Okay, this is what we mean by probability density function. Okay, again, height is 1/2 and so on. Of course, we cannot do such sketches all the time. So we are only drawing this, as I have said, the base of these boxes, and I'm telling you that, you know, over this axis, z-axis, there is this height of 1/2. Now the question is, find conditional mean, or let me say it like a problem, find the optimal estimator minimizing MSE. Find the optimal estimator for estimating y random variable given x random variable in terms of MSE, Optimal estimator, I would like to minimize the MSE and I would like to predict y from x. Okay, so how can I do this? So my estimator is, well, theta of, I'm trying to estimate, let me write y hat of x, isn't it? This is my estimator. This should be equal to expected value of y given x. Okay. That is the end of this problem. So I'm trying to estimate y from this x and so on. So how can I find this estimator? Well, again, let's assume that my x is equal to something like 1/2. If x is 1/2, maybe somewhere I'm over here, then what are the possible values for y? Okay. Well, I should calculate the conditional probability, obviously. Okay. And calculate the mean value of that conditional distribution when x is equal to 1/2. But let's see, when x is equal to 1/2, I see this slice of this distribution. Okay. And if you calculate this conditional probability, well, this is nothing but joint probability, this thing, divided by marginal probability. But joint probability is always constant. So you see that the conditional probability will be just uniform distribution. Uniform distribution in between, 0 and 1 for y. Okay. We can calculate this if you wish, but I don't want to calculate it because one more time, let me say it or write it. So I need to calculate y given x. And this is nothing but joint distribution divided by marginal distribution of x. Okay, for a given x is equal to 1/2. This is just a number. I can evaluate that number if you wish. But this is joint distribution divided by one, whatever this number is. But since joint distribution is always flat, uniform, so at the end I get a uniform distribution. So only thing that I need to understand is where this uniform distribution starts and ends. So y values, non-zero values, start when y is equal to 0 and that y is equal to 1. Okay? So when x is equal to 1/2, I have such a case. So what is the, so let me then write this. This is uniform distribution in between 0 and 1. Okay. If x is in between 0 and 1. Am I right? For any x, I have the same issue. So how about this one? If x is in between -1 and 0, the other part, x is in between -1 and 0. Now I have uniform distribution between y is equal to -1 and 0. So y is equal to, when I set my x, so this is in the third quadrant. So this is the first, this is the second, this is the third, this is the fourth. So xy positive is the first, this is the third quadrant, or if you think about the base, okay? Base of that. Now this is uniform in -1 and 0, okay? So what is the conditional mean? So this is 1/2. So would you agree that if I just write this, 1/2 times sine of x, because the mean of this one, when x is positive, is 1/2. When x is negative, the mean is -1/2. So this is, you may say, so let me draw this with, again, this color. So this is our, actually, conditional mean function. Do you remember we have defined expected value of regression line? This is this regression line. Okay? 1/2 times sine of x. So this is -1/2. This is +1/2. And I have such a case. Okay. So 1/2 times signum x, sine of x. So let's try to calculate the mean square error. So let's also calculate the minimum MSE achieved by this estimator. 1/2 sine x estimator. Okay, so how can I do this? This is what we call risk, isn't it? So I have minimized this risk. So this is the minimum value for that. Y minus y hat of x, parentheses square. Okay. So my y hat is equal to this. So how can I calculate this one? Okay, so this is an expectation for x and y. So then let me do this. This is expectation over x, expected value of y minus y hat of x okay, given x. Or let me, I think it's clear, but okay. So this is y given x. So what did I do? Again, iterated expectations. So this is the joint density of x and y. This is x times conditional density. So inner, let me see, inner, this is this one. Let me mark with different colors, or let me write this again. Expected value of x, expected value of y given x, let me also introduce this and I have this, okay? Okay, so I have something like that. Then how can so I want to introduce this. When x is greater than 0, I have something. When x is less than 0, I have something else. So I want to introduce that. So how can I introduce that? So I want to do the following. When x is probability of x greater than 0 plus x less than 0, or one of them is greater than or equal to, I have something like that. So whatever I have inside of this green thing, I will be writing it over here. So can I always do this? Expected value of something, condition on this event, then probability of this. This is nothing but the total probability theorem. Okay? So I'm allowed to do this. Now that means I can write this green inner expectation argument inside over here and over there. Okay? Well, let me try to do that then. Expected value of x, given that x is positive. So what do I have? Expected value of, okay, y given x, and I have another condition, x is positive. Okay? Y minus y hat of x, parentheses square, given x, and I know x is positive. Okay? This is closing this. This is this. Probability of x greater than or equal to, which one was equal to this, plus, so the same thing, okay, let's write this. This is this. I have that. Okay. So what else? Now, when x is positive, y hat 1 over 2. This is just 1 over 2. This is just minus 1 over 2. Okay. Because please remember, this is nothing but 1 over 2 times signum x. So for the sake of this calculation, x is fixed, and we know that x is positive, then 1 over 2, okay? 1 over 2 times signum x. So I have such a case. So how about this probability of x greater than 0? Probability of x less than 0. Now, so how can I calculate the probability of x greater than 0 or less than 0? Well, if you can calculate the probability of x marginal distribution, you get uniform distribution. Or from the symmetry, you can say that this is equal to 1/2. Okay? This is also equal to 1/2. Okay? Because if you calculate the marginal distribution of x, if you integrate over y's, you get a uniform distribution between -1 and 1. Okay? That is it. So x greater than 0 or less than 0, they have the same probability because, uniform distribution, or just from the symmetry. You can say that if I, replace x and minus x in this problem, nothing changes. So the sign, because of that, is inconsequential. So I have 1 over 2 over here. Okay. So how about this? Y minus 1/2. Now I should calculate this, inner expectation. Y minus 1/2 square. So you can see that this is an expectation over y. Okay. But for x's, conditioned on x is positive. So essentially you are taking uniform distribution. When x is positive, y is uniformly distributed in, well, again over here, uniformly distributed in 0, 1. So what we see is This is when x is positive, I have 0, 1 distribution, then this is its variance, isn't it? Because its mean value is 1/2, then its variance is this quantity. So what do I see? So I see the following. So this is expected value of, or, so let me write it over here. Now this becomes, so this is variance of uniform distribution in 0, 1. Because of this, x is positive, then y given x, uniform distribution, and this is just the mean subtracted, so indeed this is the variance definition. Then this is equal to variance of uniform distribution in 0, 1 with some abuse of notation times 1/2 plus variance of, this is the same, uniform distribution in -1 and 0 times 1/2. Okay, so what is this? I know that, okay, this is equal to 1/12 from my uniform distribution information. Okay, so the final result is then 1/12. Okay, so this becomes the MSE 1/12.